Assalamu alaikum everyone. I hope you are fine and doing well. Dear student, today our topic is matrix of linear transformation. It's my pleasure to welcome you all today, and uh, it's good to see you all here once again. Today topic is quite important since corresponding to every matrix there is a linear transformation, and whenever we are saying there is a linear transformation, there is a matrix. It's one of the fundamental theorem of linear algebra that whenever you have linear transformation, there is a matrix, and whenever there is a matrix, there is a linear transformation. Let us come up with some concept of linear transformation. Dear student, if you can look over here in this slide number 2, the linear transformation T is a transformation from n tuple to m tuple, and is defined by it can be represented by a matrix of transformation, or it can be written as a system of linear equation. Dear student, if it can be defined as W1 A11 X2, that is, it take n n n tuple, that is x1 x2 xn, x1 x2 xn. These are element of Rn, and it's map on Rn, that is W1 W2 Wm, or it can be written as an since this is a transformation from Rn to Rn, so the order of matrices corresponding to this transformation is m cross n. This is m cross n. If you can written this system of equation in term of matrix algebra, then W1, W2, W3, Wm is basically element of uh, codomain Rn, and x1, x2, x3, basically this is the element of Rn. If you multiply this, then you can say the matrix which exists in this corresponding to this transformation is of order m cross n. If this matrix m cross n is multiplied with n cross 1 column vector, then ultimately you will get the column vector which consists of m rows and one column, that is m rows and m column, and which is surely the element of codomain Rn. So one can written as W is A into X, where X is the element of domain and the W is the element of range. When you multiply A or matrix with element of domain, it will give the element of codomain with or with m cross one column vector. So this is one of the standard notation for linear transformation, that this matrix that exists corresponding to this transformation is called the standard matrix for the linear transformation T, and it is called multiply T can be obtained by multiplying just A with the element of domain, that is multiply A with element of domain, that is. So this is just this is more or less a very important relation between transformation and matrices, which I have discussed in my first slide while starting this matrix of transformation today topic. That whenever we are saying every linear transformation from Rn to Rm is a matrix transformation. Conversely, every matrix transformation from Rm to Rm is a linear transformation. It means whenever you are talking about linear transformation, it means you are talking about matrix. And whenever we have matrices, then we can say from this matrix we can form linear transformation by using a T of x is equal to A into x. So every matrix define a transformation. Let A be a what you call it as a the column vector such that A times x exists, then A define the matrix of transformation T of x is equal to A. So let us take one transformation from say R3 to R3 to R2. Means it take three tuples and map on two tuples. So in that case, we can take A as of order 2 cross 3, and in that case, if we apply T on element of R3, R3 element can be written as a 3 cross 1 column vector and is multiplied with A, that is A into X. X is the element of domain, and in that case, transformation is from R3 to R2. If you can multiply this 3 cross 1 column vector with 2 cross 3 column, you will get uh, 2 cross 1 column vector, which is the element of R2. Here, if you can multiply, take some particular element like x is 1 and y is 3 and 4, z is 4. In that case, if you can multiply a with x 1, 3, 4, then in that case 6 and 8 will be the output. You take three tuples and this map on two tuples. It means the three-dimensional space is map on two-dimensional space. It means similarly, if you can take another element 3, 1, 2, this is the element of R3, and the resultant after multiplying this element with this matrix, the resultant is 14 and 2. In that case, we can return these as that's 1 3 1 2 map on 14 and 2, that is, and 1 2 3 under transformation T map on 6 and 8. In that case, we can say here this is the domain, and domain is consist of R3. It means each and every element is three tuples, and the codomain, which is R square, it means each and every element is two tuple under these transformations. So this is one of the geometrical interpretation. So how your three-dimensional space is mapped on two-dimensional space. So, dear student, if the linear transformation T is defined by a system of equation, if you can take the coefficient matrix, that is 2 minus 3, 1 minus 5, this is a transformation from R4 to R3. In that case, as we have discussed in our previous lecture, the matrix is of the order 3 cross 4. If you can say this is the element from R5 to R4, then in that case the matrix of transformation 4 class 5. But here the transformation is from four-dimensional space to three-dimensional space. In that case, the matrix order of the matrix is 3 cross 4. So here, if you can take this coefficient matrix of this system of equation, in that case, if we can take W1, W2, W3, these are the element of codomain, and x1, x2, x3, x4 are the element of domain. In that case, if you can see if you can take the coefficient of this right hand side and make it matrix, this is 2 2 4 5 2 4 5, then minus 3 1 minus 1, then 1 minus 2 4 minus 5 1 0. So this is a matrix of a transformation, and if you want to calculate image of 1 minus 302 under this transformation T, so in that case you just multiply this element with this matrix, then you can get 3 cross 1 output is in 3 cross 1 column vector, and in that it will be in R3. So, dear student, if I can say, this is one of the matrix linear transformation. If you can take the coefficients of this transformation and place it in the form of matrices. So, in that case, if you can look over here, this is the matrix. So, matrix of transformation. This is 2. This is minus 1, and this is minus 1. Then this minus 1. Then 3, and then minus 2, then here the coefficient of 1 is 0, so 0, coefficient of x square is 2 and the coefficient of x3 is 4. In that case, we can write this transformation as a matrix. So one can say we can write any linear transformation as a matrix, as in the form of matrices. So it is more simpler and it is more adaptable in computer graphics and other image processing applications. So because in while we are discussing matrices in any programming language, it is quite easier to use as compared to any other mathematical expression. So these are just which expression is better to basically give you the better analyzation. So it depend upon situation that if you are using this in some programming language, so matrix algebra is much more better as compared to this symbolical representation. So these are a little bit. So let us come up with how the we link standard basis with linear transformation. So let T the transformation from Rn to Rm be a linear transformation such that the E1 it is E1 1 0 0 0 0. So it's a n dimensional from n dimensional vector. So if you can apply this T on this, then you will get first column vector. Then if E T of E2, it means E is a standard basis of Rn, and you can say, if I can say standard basis of R square, it means 1001. So in case of n dimensional vector space, means to say Rn, in that case the standard basis will be 1 0 so on 0 1, and that and E2 0 1 so on 0, and then En is 0 0 so on 1. So in that case, whenever you are applying T on a standard basis of first standard basis of Rn, then you will get first column vector of this matrix, and then second column, third column. If you can place all these output of linear transformation T while applying our standard basis, the output is placed on as a column vector, then this basically the matrix which we have basically obtain after applying T on standard basis of Rn. So the output will be placed in matrix form. This matrix is the basically standard matrix for T, this transformation. So if you just place this output of each standard basis in column vector, and you will get m cross n matrices, which is a standard matrix for T. So I'm not going into the proof of this. You just go through from the proof, which is quite significant. So, dear student, how to find out the standard matrix for the linear transformation, that is given in example 1. T is a transformation from R3 to R2 defined by this. So you just place the standard basis of R3 is 1 0 0 0 1 0 0 0 1. So you just ET of E1, that is a standard first standard basis of R3 1 0 0, and just put 1 0 0, that is 1, this is 0, and then 1 which is 2, then this is 0. You will get output is under this transformation. If you put input as a 1 0 0 over here in this transformation, you will get 1 2. So T of E1 is, if you apply T of E1, that is in form of column vector, is 1 0 0, and the output is 1 2. Similarly, if you can put input as a 0 1 0, the output will be minus 2 and 1. In that case, this 1 0 0, which is standard second standard basis of R3, is mapped on minus 2 and 1. Similarly, the standard basis of third standard basis, which is E3, if you can apply T on this third standard basis of R3, you will get 0 0. In that case, dear student, as you can see from here, this transformation, the matrix of transformation is of the order 2 cross 3. In that case, you just put T of E1, T of E2, T of E3. In that case, 1, 2, minus 2, 1, and 0, 0. In that case, the order of the matrix is 2 cross 3. If you can apply matrix A on the input of domain, that is matrices, you will get back the linear transformation. It means if you have a matrix and you can just apply matrix on the input of the domain, that is domain is R3. So if you can apply A with domain, which is any arbitrary element of R3, because R3 consists of three-dimensional space, so each and every element is of 3 cross 1 column vector, which is consists of three tuples x, y, z. If you can multiply A with this general element of R3 in 3 cross 1 column vector, you will get x minus 2, 2x plus 3. In that case, T of xy is to x minus 2y, comma 2x plus y. In that case, dear student, if you can say that if you have a matrix, then you can make its linear transformation. If you have a transformation, then you can make its matrix. So let us take this as a homework and produce this matrix corresponding to this linear transformation. So again, this is, dear student, one of the concept of composition of a linear transformation. So if you have, a, say, a T1 is a transformation from Rn to Rn, Rn to Rm, and T2 is a transformation from Rm to Rp. In that case, dear student, if you can look over here, so if I'm not say this one, so in that case, the matrix of a transformation is, if I can correct it, like in that case, if you can allow me, that in that case, a t like this is, if you can look this, so t is a transformation from, say, sorry. This is just a transformation from, you can see over here, this is just a transformation of what I can say. Wait. So this is just a, dear student, this is just a transformation that is, T is basically composition of a transformation. This is from Rn to Rp, Rn to Rp, and which is consist of two transformation, T1 and T2. If you can apply T1 on V, and then you will get W, and if you can apply uh, T2 on this W, you will get U. So it means T is the composition of a two element, that is uh, uh, T of V1. If you can apply T1 on V, which is the element of Rn, and then you will get W. So if you can apply W on, like if I can take that, let us say for you, dear student, I just put it, and what you will get, like you get the output is CW, and if you can apply T2 on W, you will get U, which is the element of RP. So this is just a composition of a function. So dear student, if you can look over here, so from this geometrical representation, the composition of a linear transformation is, if you have a two transformation and you just take it as a linear to composition, and composition is not defined unless the range of T1 and T2 within the domain of T2. It means I mean to say the generally, dear student, the composition is non-commutative, and it depends upon the transformation. Either composition of a linear transformation may or may not be a, you can say, linear transformation. So let us take one theorem that T is a transformation from Rn to Rm, and 2 is a transformation from Rm to Rp. The linear transform with standard matrices A1 and A2. The composition is defined by T2, T1 is linear transformation. If T1 and T2 are both are linear, then in that case you can say T is, in general, T is a the composition is basically if you apply T1 on V, and then after this output you will apply T2 on this, and this is basically the T, and which we have discussed, this is basically the T, and this is basically the composition of a function which is consists of T1 and T2. If you apply T1 and then T2, this is equal to if you apply T from V to U. So, dear student, uh, let us the standard matrix for of uh, T, which is A for T is given by the product A, which is A2, A1. In that case, the this is A2 is the standard matrices of T2, and the A1 is the standard matrix of T1. So the because T is the composition of a two functions, so its standard matrix is also a product of two matrices. Look over here. We have two transformation from R3 to R3. So we need to calculate the matrix of transformation corresponding to composition of T1 and T2 and T dash, which is T2 and T1. It means you have first apply uh, T2 on some element of V3, then apply T1 on some the output of this. So let us take two transformation. This is T1. This is apply on X, Y, R3 element, and this is again it will the output is also in R3. So T2 is also a transformation from R3 to R3 because it take three element and map on also three tuples. So the corresponding, if you can look over here, the matrix of transformation is 2, this is, and y is 1 and z is 0. So in that case 0, 0, it means x, all the coefficient are 0. So in third order pair, if you can look, the coefficient of x is 1, the coefficient of y is 0, and the coefficient of z is 1. In that case, corresponding to T1, the A1 is the matrix of transformation corresponding to T1, and 2 is the similarly the matrix of transformation corresponding to linear transformation T2. So we have to calculate the uh, matrix of a transformation corresponding to T. In that case, A is A1 and A2, and in case of T dash, this is A2 and A1. This is the matrix of transformation corresponding to T dash, and this is the matrix of transformation corresponding to T, which is the composition of T1 and T2, and T dash is the composition of T2 and T1. So dear student, inverse linear transformation is fundamentally depend upon either some transformations are one-to-one onto. Dear student, it depend upon the matrix of a transformation. If we have transformation from T1 from Rn to Rn, and T2 is again from Rn to Rn, our linear transformation set that T2 and T1 of V is equal to V, and T1 V2 of V is equal to V, then T is called inverse of T1, and T1 is said to be invertible. So we have one theorem that if T is a transformation from Rn to Rm, in here you can see over here the input and output are same. n tuples are map on n tuple, the linear transformation with the standard matrix A, then the following condition are equivalent. T is invertible, T is isomorphic, it means one to one and on to. T is invertible. If T is invertible, if it means T is invertible, I mean to say the matrix corresponding to T, um, the matrix of transformation which is non-singular, or I can say A is invertible, I mean to say matrix T is inverted. In that case, these are all equivalent. If any transformation, if T is invertible, it means the matrix corresponding to this T will be invertible. If A is invertible, it means its determinant is non-zero. In that case, T transformation is invertible. Because why all these happen? Because when we are start our lecture, I told you that whenever you are talking about matrix, there is always a linear transformation, and whenever you are talking about linear transformation, we are always talking about matrices. So matrices, whenever we are saying corresponding to every matrix, there is a linear transformation, and corresponding to every linear transformation, there is a matrix. So how to find the when all these if one of the condition is hold, the other are equivalent to it. So if I can say T is inverted, it means T is isomorphic and T is A is invertible. Whenever I say T is isomorphic, it means T is invertible and T is A is invertible. And whenever I say A is invertible, it means T is invertible and T is isomorphic. So, dear student, let us find out the inverse transformation of this linear transformation, that is from R3 to R3. Let us find out the matrix of transformation corresponding to this linear transformation. Since we make the transformation from this transformation, so the matrix of transformation is this one. If you calculate the determinant, it is always non-zero. It means this is a non-singular matrix. We calculate its inverse. So if you can multiply the inverse uh, A inverse with any journal element of R3, any journal element of R3, I mean to say X, Y, Z, which is consists of three class one column matrix like this one. V is any element of R3. So T inverse V, I means to say I have to apply the T inverse, I means to that I have to multiply A inverse with X column vector, that is three class. If you can multiply this, then you can easily get the inverse transformation of the transformation which is given over here. So this is inverse transformation. Because why this happened? Because if you can look over here, the determinant is non-zero. So, dear student, these are just, if you can look over here, the determinant in this case is non-zero. In that case, dear student, this is not invertible. So, T of a transformation from R4 to R4 is not 1 to 1 and on to. So, dear student, this is all about our today lecture. Thank you all, and please stay at home. Uh, and may Allah bless you uh, with healthy life, and that's all about. Allah Hafiz, and please stay at home.